from current slide. Okay. All right, before we get going, I don't know of any major announcements. I think my office hours are going to be pretty much normal for most of the rest of the term, I hope anyway. On Mondays and Wednesdays, that's 3:15 to 5:15. On Tuesdays and Thursdays, 1:15 to 3:15. And on Fridays, 7:45 to 11:45 on the Birmingham campus. Okay. Any questions on anything we've done so far?
Everything.
Okay. Be specific. All right, well then here's where we left off last time. We were solving equations with trigonometric functions, equations. What's the technique? What's the procedure that we use for something like this? In most equations, what's the goal? Solve for x, exactly. Isolate the variable, right? In trig functions, you first isolate the function, then solve for the variable. Okay? So there's just another little step in there. We first manipulate the trig function and use the same techniques you would if it was just a plain variable, and then once you get figured out what the trig function is, then solve for the variable x. So what would you do first on this one?
Subtract the sine at x over.
Do what now? Say it again.
Subtract the sine at x over.
Okay, let me get Brittany here.
Oh, yeah,
Okay,
subtract the square root of 2.
so you're saying subtract this sign from both sides? Is that what you said?
Subtract the square root of 2.
Okay, that is one thing, and that's what you want to do first, right? Okay, subtract root 2 from both sides. And what does that give you? What does that give you?
Negative sine x minus
Sine x is equal to negative sine x minus root 2. Okay? Now what?
Solve for the functions, and then solve for x.
You got to get all your sine x's on one side.
Oh,
just like you had to do x's, right? Delta is here.
You add sine x back.
Yes, add a sine x to both sides. Okay? Now what do we have? 2 sine x is equal to negative root 2. All right? Now what? Solve for sine x. Solve for sine x. So what would you do? Divide by 2. Very good. Okay? The 2's go out. So now we have the sine of x is equal to minus root 2 over 2. Now, what's that? Okay, I couldn't hear what you asked. Yeah, we're not doing identities. We are solving trigonometric equations. Okay? And these are conditional equations. Section 5.2 was verifying identities. This one is solving trigonometric equations. So yes, we are crossing the equal sign. I have one, but I think it's out of staples, I think. Yeah, I'll try to get more. What I'm going to do, I'm going to put your page in the middle So it's going to be held by that staple. Okay. Okay. So now, at this point, we ask ourselves what values of x will make this true. So now we're looking for x. First solve for the trig function, then solve for the variable. So what values of x, what angles x will give you a sine of that angle would be negative root 2 over 2.
It has to be the
Third or fourth quadrant. Exactly. What would be your reference angle?
45 degrees.
45 degrees, or if you're dealing in radians, 5/4. So in the third quadrant, what would that be?
7 power 4.
So again? You might have said it. What?
7 power 4.
Okay, that's in the fourth quadrant. So that's one answer. And in the third quadrant, 5 power over 4. Okay? So we get from there that x is equal to 5 pi over 4 or 7 pi over 4. But since they didn't put any restriction on this, we have to, what is the period for sine? 2 pi. So you put plus 2n pi. Plus 2n pi. Where n is any integer. Okay? That allows you to go 1 time around, 2 times around, 3 times around, or backwards a few times, or however many. But every time you cross that, you would have that. So those are two possibilities. 5/4 pi plus 2n pi, or 7/4 pi plus 2n pi. That's a really ugly 7, isn't it? So let me clean that up just a little bit. Okay, that's a little bit better maybe. Ooh, I'm getting it worse. Okay. And if you'll check in the text, you'll see that's exact. Well, we're going to have it coming up here. All right, to erase this?
Yeah.
Okay. So let's see how they did it. All right, they wrote it down again. Okay. So what we start off with when we're solving trigonometric functions, solve first for the trig function, then figure out what the variable is. Whereas the regular solving equations, you solve for the variable. Here you solve for the function, and then solve for the variable. Okay? So here they wrote it down again. And what they did, they first added the sine x to both sides. Okay? And next they're going to combine like terms. Well, no, they're not. Subtract square root of pi. Square root of 2 from both sides. And then they combine like terms. They sure take their time with it. 2 sine x is equal to negative root 2. And then divide both sides by 2. And that isolated your sine x. Sine x is equal to negative root 2 over 2. Well, we know that's one of our favorite ratios. That's going to be your pi quarters ratio. And you're going to be, they say, let's first solve it in the first period, 0 to 2 pi. And that would be 5/4 pi and 7/4 pi. And then add multiples of 2 pi to that, 2n pi plus 2n pi to each of those. There's your general solution where n is any integer. When n is 0, you have 5/4 pi and 7/4 pi. When n is 1, you have one more circle around. And when n is -1, you have a circle that way. And you can do as many integers as you want, positive or negative. Any questions on that? You see how it works? Okay. Now, they're skipping example 2, so let's us go back and do example 2. Okay. Example 2 is 3 tangent squared x minus 1 is equal to 0. Okay? There's an equation, and by the way, this is not an identity, this is a conditional equation. So we want to find what values of x will make that true. That's what conditional equation you do with it. Conditional equations. What would be your first step? How can you factor that? Okay. The square root of 3 tangent x minus 1 square root of 3 tangent x. If you're going to do that, you have to take a square root of this. Is that what you were meaning? Okay. You could do it. That would be right if you took a square root of 3, but not 3. If that were 9 tangent squared, then the square root of that would be 3 tangent. Yeah, 3 tangent. You could do it that way, for sure, and you're going to get the same answer. How would you do it without taking that? Remember what we said before? Solve for the trig function. And what would that be? Second? Say it again. My hearing's bad, I can't hear. Okay. Yes, but this is a 3 tangent squared. If you didn't have this, it's not quite. Tangent squared x plus 1 is secant squared. Okay. So don't make up new identities. Okay. No. Yeah. Huh?
Are you going to divide the 3 over?
Almost. First, add 1 to both sides. Okay. Solve for this. So add 1 to both sides. And that gives you 3 tangent squared x is equal to 1. And now, divide by 3. Okay? And that gives you tangent squared x is equal to 1/3. And then what? Take the square root. That would give you tangent x is equal, say equal to and write a plus sign. What is wrong with you? Okay, don't answer that question. Okay, all right. When you take the square root of both sides, what do you get? Okay, you get plus or minus. Anytime you take the square root of both sides, you have to do plus or minus, and it'd be 1 over root 3. Or, I think you were saying plus or minus the square root of 3 over 3. Is that what you said? Yeah. All right. Now, what values of x would give you, let's start with the plus one, root 3 over 3. Second. Pi 6. I believe you're right there. So x is either pi 6, okay? Is it pi 6 or pi? Yeah, that's right. Yeah, okay, pi 6. That will give you the plus. What would have given you the minus?
11 pi 6.
Okay, very good. Let me get Whitney here and Cheston here. Okay. And Mike is here. All bundled up. Got some shit. Okay, I know you're in. There you are. Okay. All right. Filling up a little bit. So, the pi 6 will give you the plus root 3 over 2, and the other would be 11 pi 6, 1/6 1 pi 6 short of 2 pi. Okay.
Isn't it all of them that are positive or negative?
What's that now?
Isn't it all of the tangent values that are for real? Or is it just one positive?
Okay. I was just, okay. If you think about your tangent function, you can think about any one of two ways. I think usually this way, and I would have said minus pi 6 and plus pi 6. Minus pi 6 would have made it the minus and the other. Now, I don't know if what you're asking, okay, this is Terrell? No, huh? Jeremy. Okay. All right. But like I was saying, I think of it in terms of negative pi 6, it gives it the minus root 3 over 3. But that's the same as 11/6 pi if you do it over here. Okay? Now,
In the book they have 5, 6, 5.
what's that?
In the book they have 5, 6, 5.
I can't read.
In the book they have 5.
Okay, yeah. Okay, I'm getting to that next. Okay. I was doing because of what was said here. Let's graph the tangent function. It's something like this. Remember, vertical asymptote at minus pi halves and positive pi halves. Okay. The next cycle does like this. Well, not drawn too well. Okay. And you have another vertical asymptote at 3 halves pi. Okay. Now, what like you said, the book has 5, 6 pi, which is okay. This point right here, what is the period for pi? I mean, the period for tangent. I just gave it away. Pi, okay. So this is at pi again. So you're 1/6 pi short of pi, which is 5/6 pi. So here's the other place, okay? So here's the one he said, well, actually it'd be one more over, okay? And it would be here, but it's also there. So it doesn't matter which one you did. I would have said negative 1/6 pi. He said 11/6 pi, that's just short of 2 pi. The book said 5/6 pi. All those are the same because guess what we're going to do to these? We're going to do plus, what's the period you said? Pi, so it'd be plus n pi. And this will be plus n pi. Now, if your n happened to be a -1, right? That's an n, a legitimate n. Then you subtract 6 pi from that and you get 5/6 pi. So yeah, you're going to get every one of those. Subtract 2 n pi from that, you're going to get the minus pi/6. It'll cover them all, okay? So yeah, the book has 5/6 pi. I would have said negative 1/6 pi. He said 11/6 pi. When you add the n pi, that picks up every one of them, okay? So it really doesn't matter for sure which one you do, but that will be, it'll get them all. To get the one the book did, they did the first positive one here for the pi/6, and then they did the next positive one would be 5/6 pi here. But I would have gone back here and said negative pi/6. He went all the way over here and said 11/6 pi. All those are correct answers. They all are at -1, and when you put the plus n pi, you cover them all. So it really doesn't matter. All those are legitimate answers. But the book does have 5 pi/6. Okay? So, let's clear our chicken scratch out of the way. You see what I'm saying there? They're all equivalent answers, okay? Oh, I'm sorry. It doesn't have it on the slide set, sorry. So yeah, they said pi 6 plus n pi, that gives you your plus root 3 over 3, and the minus is given by either 5/6 pi plus n pi, or negative 1/6 pi plus n pi, or even 11/6 pi plus n pi. Any one of those will produce the correct answer. Okay. They also leave off, if I'm not mistaken, yeah. They also leave off example 3. So let's do example 3. Here's an equation. Cotangent x times cosine squared x is equal to 2 cotangent x. Okay. Chelsea. Okay, I was just going to say that. Okay. Now, what looks a little bothersome about this one? You have both cotangents and cosines in it. It's going to be hard to isolate one or the other, but actually not as hard as you might think. So what might we do first before we start? Give it a shot. Okay, which way are you doing? Are you going, when you say move it, how do you move it? Second? Okay, now that cotangent and cosine are multiplied. Oh, okay, move this way. You're going to subtract this from both sides. The two, okay, got it. Okay. That's why I wanted to make sure. Minus 2 cotangent x from both sides. All right. So that gives you a cotangent x cosine squared x minus 2 cotangent x is equal to 0. Okay, because that side goes to 0 now. Now what can you do? Factor it. And what do you factor? Okay, factor out a cotangent, and that would be cotangent x times cosine squared x minus 2 is equal to 0. Is that right? All right. Now, where would you go from here? Say again? Okay. So either cotangent x is equal to 0 or cosine squared x minus 2 is equal to 0. Okay? Now, what values of x will make cotangent equal to 0? Think of it this way. What is cotangent? In the quotient identity or ratio identity? Say again? Okay, but I said in their reciprocal identity, not reciprocal, your quotient identity is a ratio identity. It's what? Cosine over sine. So the only way for cotangent to be 0 is for cosine to be 0, right? And where is cosine equal 0? Your half pies. Every one of your half pies. So this is going to be true when x is equal to pi halves. And what cotangent, what's its period? What's the period of cotangent? So this will be plus n pi. Okay? Every half pi, you're going to have a cotangent equals 0. Very good. How about the right-hand equation? What can you do there? Second, add 2 to both sides. And this tells you that cosine squared x is equal to 2. Second, take the square root of both sides. Okay, so that will give you cosine x is equal to, but now you have to do plus or minus the square root of 2. Okay, what values of x will give you, if you take the cosine of it, will give you square root of 2 or minus square root of 2? Is that one of our favorites? No. In fact, is that one of ours at all? Why not? What is square root of 2 approximately? 1.414 approximately, right? When is cosine ever 1.414? Never! Okay? You cannot have this cosine being anything outside plus or minus 1. So, plus 1.4, nope. Minus 1.4, nope. That does not have a solution. No values for x. So our only values that make this true are that one. Okay? They drew a graph of it, which I never would have thought of doing, but, you know, it's perfectly fine to draw the graphs if you like. Okay? That's because they have graphing calculators that will draw them for it. And by the way, folks, remember, every one of these examples is followed by a checkpoint, and it would be a great idea to check out your checkpoints. I would say as soon as you get out of class and have some free time, try to do those checkpoints. All right, now finally we're ready for equations of a quadratic type. Okay? Well, some of these have been equations of a quadratic type. So many trigonometric equations are of quadratic type. Ax squared plus bx plus c equals 0. With now, instead of the x's, you have some trig function. Okay? Like sine squared, or cosine squared, or tangent squared, or secant squared. Usually not too many cotangent squares or cosecant squares, but you could have them. Okay? So those are what you have there. So here's a quadratic one in x. 2 times sine squared x minus sine x minus 1 is equal to 0. What do you think your first step would be for one like that? What's the F word? Factor. Okay? This would factor as 2 sine times sine. Okay? This factors as plus 1 and minus 1. And see if you can combine those any way together, your signs and your placements of the 2 and the 1 to see if they will factor. Okay? And that's exactly what they did here. This and this mean the same thing. Okay? This one, everything in secants, try factoring. Secant squared times secant squared. Okay? And this one would be either plus 1 and minus 2 or minus 1 and plus 2. One or the other. Factor it and see what you get. Okay? So to solve equations of this type, factor the quadratic, or when it's not possible, you can still use quadratic formula here. Okay? Only then you would have, rather than x equal, you'd have sine x equal, or secant x equal. Minus b plus or minus the square root of b squared minus 4ac all over 2a. You use the same deals that you did before, only now you're solving for sine or secant or whatever your trig function is. You can use that in quadratic formula as well. Okay. Let's do example 4. Find all the solutions of this quadratic equation in sine on the interval excuse me, between 0 and 2 pi. Man, I'm having trouble breathing. So, what would you do first? I hinted at it before. Factor. I did more than hint. Okay, now when do you factor, by the way? You factor when one side is equal to 0. It doesn't do any good to factor if that side over there is 17 or 3 or 4 or 8 or 5. Anything other than 0, don't do it. Get numbers over here, make it equal to 0, then factor. Because we have a 0 product principle, we don't have a 17 product principle or a 4 product principle or anything else. So what are your possible factorizations? 2 sine squared will only factor as sine x and 2 sine x, okay? And minus 1 will factor as either a plus 1 or a minus 1. Any preference on where you're going to put it? Plus 1 first, minus 1 last. Let's see if it works. Okay? Sine x and 2 sine x, sure enough, is 2 sine squared x. That's the first in boil. The outer is minus sine x plus 2 sine x would be minus sine x plus 2 sine x would be plus sine x. What's wrong? This is right, the sign's wrong. So if the sign's wrong, change your signs. Okay? Make this the plus and make this the minus. Okay? Alright, let's go back and try it again. First, this sine x, not 2 sine x, is still 2 sine squared x. That's good. Now you get plus sine x minus 2 sine x gives you minus sine x, and then you have a minus 1. Yes, that's the correct factorization. Okay, what do we do from that? Okay, so each of those equals to 0. So this says that either sine x minus 1 is equal to 0, or 2 sine x plus 1. That's supposed to be a sine x, not 6, okay, is equal to 0. Okay, let's solve the first one. How would you do that? Add 1 to both sides, and that gives you sine x is equal to 1. What values of x will make that true? Where is sine x equal to 1? Say again? I can't hear. At 2 pi, it's the same as at 0. Sine is 0 at both of those. Sine starts at 0 and then goes up to 1 where starts at 0 here, goes to 1 at what's that? Okay, not third quadrant. Right there.
First quadrant.
Okay, right there. Pi halves. Okay? Because the opposite side is sine. Here it's 0, here it's 1. Okay? So this is at pi halves. So x equal pi halves. And that is the only place between 0 and 2 pi where it is 1. If you drew that sine function that starts at 0, goes to plus 1, back to 0, to minus 1, and goes back to 0, the only place it's equal to 1. And since they limited you to that domain, yeah, that's it. So let's go to the second equation. And what does it give you? What would you do there? Subtract 1 from both sides, okay? And that gives you 2 sine x is equal to minus 1. And now what? Divide both sides by 2, and that gives you sine x is equal to negative 1/2. And where is that true? Negative pi what? Negative pi 6. Okay, but negative pi 6 is not in that domain. Oh, Terrell is here. Okay, what is the value that is in that domain? What's the equivalent in theory to pi of negative pi 6? It's what? 7/6 pi is absolutely correct. Okay, so x could be 7 pi 6. In other words, that pi 6 being your reference angle past, because remember, sine is positive in the first and second quadrant. It's only negative in the third and fourth quadrant. So pi 6 past the horizontal, which is past pi. So 1/6 plus 6/6 is 7/6 pi. But the other place is 11/6 pi and 11/6 pi. All right. So on the interval from 0 to 2 pi, those are your three places where this equation holds. Okay? You don't need your plus 2n pi or anything like that now because you're only limiting to one period. But you got to list every one in that period. And there they are. All right. Okay, let's see how the book did it. Okay, first thing they did was write the equation again. Good for them. Okay, write the original equation. Okay, then they factored it. 2 sine x plus 1 times sine x minus 1. Set each of those equal to 0. 2 sine x plus 1 equals 0 will yield sine x equal negative 1/2. And sine x minus 1 equals 0 yields sine x equal 1. Over on the left, two values that happens to, you know it's going to be pi 6 is going to be your reference angle because that's where sine is 1/2, but it needs to be a minus 1/2, so it can't be in the first quadrant or second quadrant because sine is positive in both of those. But pi 6 past the horizontal, that would be 7/6 pi, and pi 6 from the horizontal in quadrant 4 would be 11/6 pi. 1/6 pi short. Yeah. There. That one is, and then sine x equals 1. Only one time that happens between 0 and 2 pi, and that's at pi halves. Okay. Does that make sense? All right. There's example 4. Now they do show what they're calling, a graphical solution. And the trouble with those are they give you decimal numbers. They don't give you pi 6 and pi 7/6 pi. And sometimes it's really hard to recognize the decimal number out of the other. The pi halves is sort of easy because you know what pi is, 3.1459, and half of that is 1.757, blah, blah, blah. So, most of the rest of the time won't be that obvious. And again, checkpoint after every one. All right, they're going to skip example 5 and 6. So let's do those two. All right. Goodness gracious. Getting all clogged up here. Okay. Let's do 2 sine squared x plus 3 cosine x minus 3 is equal to 0. What's wrong with this picture? You have sines and cosines. That's not very good. It's hard to isolate one or the other. You got to figure one. So the question is it easier to get sine squared into some expression of cosine, or to get cosine into some expression of sine? You want to get sine squareds into cosines? I agree. Why? Your Pythagorean identity does exactly that. When you got a square, think Pythagorean identity. So what is sine squared in terms of cosine? Squared. 1 minus cosine squared. Okay? So instead of sine squared, we put 1 minus cosine squared. Then we have a plus 3 cosine x minus 3 equals 0. Okay, I hope I copied the problem right. Did I? Yeah, I think so. Okay. Now what do we do? Okay, distribute the 2 across, and what does that give you? 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Okay, everybody agree? Now what do we do? Louder. Combine like terms. What like terms do you see? 2 and a negative 3. So that will give us a negative 2 cosine squared x plus 3 cosine x. Say again? Minus 1 equals 0. Now, is there anything you don't particularly like about the way that looks? Anything? And this is just my little picky, icky thing. I really don't like having my leading coefficient negative. Now, if this were just an expression, we'd live with it. This is an equation. Now, what can we always do with an equation? Multiply or divide or move it around, whatever you want to do, as long as you don't multiply or divide by 0. But let's just multiply everything on both sides by minus 1. That's legal, right? Do the same thing on both sides. It's okay. So what that's going to do is make this a plus, that a plus, and make this one a minus. And you can make it a minus 0, but who cares? It's still 0. Okay? So that was a sleight of hand. Okay? But it's legal with equations. If that was just the expression, no, you can't change that. If it was the expression said factor, you're going to be stuck with that minus sign. But since it's an equation, you can do that. You could have, if you didn't want to multiply, you could have added 2 cosine squared x to both sides, subtracted 3 cosine x to both sides, added 1 to both sides, and then you wind up with this exact thing. So yeah, there's many ways to do it. What do you do once you have it in this form? Factor it. And how would that factor potentially? 2 cosine x and cosine x. All right. Now what does, once you factored the first term, I then look at the third term, but I first look at the sign of the third term. What is it? What does that tell you about these two signs? They got to be the same. Since something's negative, they both got to be negative. So that's going to be minus minus. Okay. And what's the only possible factorization of 1? 1 and 1. We don't know if this works or not. Let's see if it does. 2 cosine x and cosine x is certainly 2 cosine squared x. 2 cosine x times minus 1 is minus 2 cosine x. Minus cosine x, that's minus 3 cosine x. Yes, minus 1, plus 1, minus 1 times minus 1 is plus 1. Yes, that works. So we have factored correctly. So now what do we do? Set each of them independently equal to 0. So either 2 cosine x minus 1 is equal to 0, which that produces what? What's that? I can't hear you. Okay, yeah. Cosine x equal 1/2. And what value of x? Now, they didn't tell you on this one, did they? No, it just says solve it. It didn't give you any interval on which to solve it. So you're going to have to do, so where is, what's that? I can't hear you. Pi thirds, okay? So this will be x equal pi thirds, okay? That's one place where cosine x is 1/2. I first think of where cosine is positive. First quadrant, that's pi thirds, and fourth quadrant. Where would that be in the fourth quadrant? Hint, same reference angle, pi thirds, but now it's pi thirds below the horizontal, positive horizontal axis, right? It's what? Okay, we're talking in thirds though. 5 pi over 3, just short of 2 pi, which would be 6 pi over 3. So this will be 5 pi over 3. Okay, but since we're dealing with no interval here, what do we need to put? Plus 2n pi. Plus 2n pi. Okay, that just deals with the first one. We still got the second one to go. Where is cosine x minus 1 equal to 0? Yeah, that's cosine x equal 1, and where's that true? Say again? On the whole part, I don't understand. Oh, yes, okay. Not quite. It's on the even pies, even whole pies. It's at 0, 2 pi, 4 pi, 6 pi, 8 pi. Because remember, at pi, it's -1. Starts here, goes down. At pi, it's -1. Then it comes back up to +1. So that's only true at the even pies. And this will be basically 2n pi. All the even pies, 2n pi. X equals 2n pi, I should say. I'm running out of board here, sorry about that. So here are the 3 possibilities, but there's an infinite possibility. 2n pi, pi thirds plus 2n pi, pi thirds plus 2n pi. And that is what you see, bottom of page 367, 2n pi, pi thirds plus 2n pi, and 5 pi thirds plus 2n pi. Okay, and again, there's a checkpoint after every one of these, so please try to do those. All right. Everybody see that? Can I go and erase this and move on to the next? Okay. All right, the next one is example 6. Okay. Find all the solutions, and here's Justin. If I can get my pinboard. Okay. Still missing Taylor, Doc, Taiwan, Tanisha, Okay. Oh, man. Example 6. Find all the solutions of this. Cosine x plus 1 is equal to sine x in the interval 0 to 2 pi. Counting 0, but not counting 2 pi. Uh-oh. What's wrong with this one? Anything? Goodness, my hands are so cold. You got sines and cosines in it. Now, if one of those are squared, we'd be happy campers, because there's a Pythagorean identity that relates those. But neither one of them are squared. And there aren't any other useful identities that really relate sines and cosines. Yes, let's square both sides. Warning, warning. Anytime you square both sides of an equation, anytime, whether it's a trig equation or a general algebraic equation, you may be introducing some extraneous roots. So that means, and it probably wouldn't have been a bad idea all along, but that means you better check all your answers and make sure they fit the original equation as well as the squared equation. So let's do what was suggested and square both sides. And what does the left-hand side give you? Cosine squared x. Say again? Oh, you left out some cross terms. Plus 2 cosine x plus 1. Okay? Everybody see that? If you don't, think of cosine squared as this. Cosine plus 1 squared. That's cosine x plus 1 times cosine x plus 1. That's what it means to square something, right? To multiply it by itself. And then when you FOIL this, there's your cosine squared, and there's your plus 2 cosine x, and there's your plus 1. So yeah. Goodness, my head hurts. Now, the right-hand side is sine squared. The left-hand side is all in terms of cosine. So what might we want to do to that sine squared? Say again? Okay, and what would that be? 1 minus cosine squared x. Fantastic. We now have an equation with only cosines in it. So what would be our first move? Solve that equation. Yeah, add cosine squared x to both sides. I don't know why this isn't writing. Cosine squared x to both sides. Okay, and what does that give us? On the left. 2 cosine squared x plus 2 cosine x. Okay, anything else you want to do here? Don't really want it equal to 1, you want it equal to 0. So let's go on and subtract 1 from both sides. Is that okay? And then this gives you, goes to 0, that goes to 0, that goes to 0. So you're left with a 0 here. Ha! What can we do to this? Factor what? Yeah, let's factor out a 2 cosine x. And what do you have left? Cosine x plus 1. And that's equal to 0. Okay, and by the way, we're doing this on the interval 0 to 2 pi, just like this one. Okay, remind us of that. Okay? So, let's take the first factor. 2 cosine x equals 0. What does that produce? Huh? No. X equals 0, cosine would be 1, and 2 cosine would be 2, not 0. Okay? Doing the first factor here equals 0. 2 cosine x equals 0. Sine x is 0 at 0. Cosine x is 1 at 0.
Oh, I thought you meant what you give in the equation.
Oh. Okay, what do we do with this? Second? Okay, yeah, you certainly can divide by 2. Okay? And this is still 0. And this now is 1. Okay? So now we have cosine x is equal to 0. What values of x will make that happen? Your half pi's, all of your half pi's. We're only going from 0 to 2 pi, so how many half pi's you got in there? X equal pi halves and one more, 3 halves pi. And then you get past 2 pi. Okay? So let's go to the second one, and that's this one. Cosine x plus 1 is equal to 0. And what would you do here? What would you do to that? Subtract 1 from both sides, okay? And that gives us cosine x is equal to negative 1. And where is cosine x equal to negative 1? At pi. And that's the only place it is between 0 and 2 pi. So this will give you an x equal pi. All right, so there are our 3 possible solutions on this interval at pi halves, at pi, and at 3 halves pi. Those are the only 3 places where that one will be solved. Oh, except what have we better do? Check your answers in the original problem. Let me write the original problem down again. In fact, what I'll do is erase what we did to it. Okay? Remember, anytime you square both sides of an equation, you've got to check your answers and make sure they still work. Okay? Which one you want to try first? Pi halves, pi, or 3 halves pi? You tell me. Pi halves. Okay? What is cosine of pi halves? 0. Okay? 0 plus 1 is what? And what sine of pi halves? 1. Okay, that one works. Pi halves certainly does work. Okay? Which one you want to try next? Pi or 3 halves pi? You choose. Huh? 3 pi halves. What is cosine of 3 halves pi? Second? Cosine of 3 halves pi. You cold back there too. I am cold up here. Okay. What's cosine of 3 halves pi? Anyone know? See, what is the name of this course? Oh, trigonometry. We probably should know, shouldn't we? What's cosine of 3 halves pi? Zero. Okay. And 0 plus 1 is what? What is sine of 3 halves pi? Negative 1. 3 halves pi does not work. How about pi? What is cosine of pi? -1 plus 1 is 0. What is sine of pi? 0! That one works. So these two work. The pi halves and pi, the 3 halves pi doesn't. It looks like it did, but here's why it did. Because when we squared both sides, what was a -1 here, we squared and made it a +1. And then that worked. But that wasn't what the original problem was. It won't work for that. Okay. Anytime you square both sides of an equation, whether it's a trig equation or any kind of equation, you've got to check all your results and make sure that they make sense. Okay. All right. Now let's move to, to move off of this. Okay. Functions involving multiple angles. Okay? We've had situations where you have multiple answers for a given equation. This time we're going to have functions that have multiple angles, okay? Which almost sounds like the same thing, but it's not quite. The next two examples, it says the next example here, but in the book it says the next two examples, involve trigonometric functions of multiple angles of the form cosine kx and tangent kx. Okay? To solve these equations, here we have to put in an extra step. Let's back off in our thinking for a minute. When we're solving just a regular algebraic equation, isolate the variable, solve for the variable. That's what you're doing. When it was a trigonometric equation, the first thing you do is solve for the trig function, then figure out what values of the variable. This time, you solve for the trig function, then you solve for the ku, and then you solve for u. So now you have three sort of steps in there. There may be multiple steps in various parts. But to solve these equations, first solve the equation for the trig function, then for ku, and then divide by k to get what u is. Or ur, not whatever. Okay. So let's do example 7. 2 times the cosine of 3t minus 1 is equal to 0. Where do you start? Where do you start? A little louder? Okay, yeah. We're going to isolate the cosine function. So we add 1 to both sides, and that gives us 2 times the cosine of 3t is equal to 1. Okay, now what? Divide both sides by 2, because we're trying to isolate the cosine function. Okay, so this gives us cosine 3t is equal to 1/2. All right. Now we've isolated the cosine function. Step 1 achieved. Now we figure out what 3t is. Okay? The cosine of some angle is going to be pi halves. Now they didn't give us any restrictions on this. We're going to assume this is all real values here. Okay? So cosine of some angle is 1/2. What would be possible values for that angle? Where is the cosine 1/2? Pi what? Pi thirds. That's one place anyway. Okay, so 3t is equal to pi thirds. Okay, now since there's no restriction here, that would also be plus 2n pi, because cosine has a period of 2 pi. But remember, cosine is positive not just in the first quadrant, but also in the fourth quadrant. So what would be an equivalent angle, one whose reference angle is pi thirds in the fourth quadrant? 5 pi thirds. Perfect. So 3t could also equal 5 pi thirds plus 2 n pi. That gets them all, right? But we're not really looking for 3t. We want to know what t is. But it's pretty simple now. What? What do we do? Divide everything on both sides by 3. Divide this by 3, divide that by 3, divide this by 3, divide this by 3, and divide that by 3. Okay? This will finally give us our t is equal to, and pi thirds divided by 3 would be pi ninths plus 2 thirds n pi. Okay? Or over here, t would equal 5 ninths pi, okay, plus 2 thirds n pi. There we have it. Say again? I can't hear you. Okay. My hearing's so bad, I'm sorry. Okay. Do you see how that works? First solve for the trig function, then solve for the argument of the trig function, and then solve for the variable. Okay? 3 solves here. Okay. Does that make sense? Everybody see it? Again, every one of these examples has a checkpoint right after it, so when you get a chance, first opportunity, try to work these checkpoints while it's sort of fresh on your mind. Okay? Everybody got this one so far? Everybody? Okay. All right, to erase. All right, let's see how they did it. Okay? All right, good deal. Thank you. All right, good deal. You can just put it inside and do it. My stapler's out. I've got to remember to bring some up here. Okay. So here's how they start. They write down the equation again. They solve for cosine by adding 1 to both sides and dividing 2. And now they solve for cosine. Cosine 3t is equal to 1/2. Then they figure what angle 3t has a cosine of 1/2. And let's just start with the first period. That's at pi thirds, or in the fourth quadrant, 1/3 short of 2 pi, which is 5 pi thirds. But because there's no limit here, we're not just limiting ourselves to the interval 0 to 2 pi, but for all times, for all values, then you add to both of those plus 2n pi, because cosine has a period of 2 pi. So add as many periods as you want to, or subtract as many periods as you want to. Those give all those terminal angles. Well, this gives you what your 3t is, the argument of the cosine. To get what t is, you actually divide by 3 then, and that gives you pi ninths plus 2 thirds n pi, and 5 ninths pi plus 2 thirds n pi. They call that the general solution. Okay. Any questions on that? I think they skipped example 8. Are we going to have time for example 8? Huh? It looks like maybe not. Okay? So we'll start example 8 next time. We almost finished 5.3. Hopefully we will next time. Let me give you some homework assignments in 5.3. Do any of the odds 5 through 9. Do any of the odds 11 through 23. Do any of the odds 25 to 37. and any of the odds 39 to 43. Okay? We can stop there. We'll pick up the rest of those next time. Okay? Any questions? Good deal. Thank you. All right. Okay. If there's no questions, sorry I cheated you out of 2 minutes of your tuition dollars today. I'm so sorry.
They have it open for registration. They have it open for registration next spring. They open today.
Oh, they did open
Yes,
today.
I signed up for physics, but I don't know what physics is.
But what?
I signed up for physics with you,
Okay.
but I don't know what physics is.
Okay. Okay. Let me
Yeah,
end
they
this.
open today.
Oh, I didn't know.